So at the 3.4, we're solving exponential and logarithmic equations. So we're going to use some of the properties that we've already learned. And two of the major things that we'll do is, one, write one as an exponential or reverse it and write it as a logarithm. Sometimes just rewriting it is going to give us an answer. They do list the properties here for us, or a couple of them that we might use. Use one-to-one property if possible. So we might use some properties like squish logarithms together. And then we can have logarithm on both sides, use one-to-one. Rewrite it. 2 and 3 are basically the same thing. Rewrite it in the other form. So, example number 1. When the variable is in the exponent, there's nothing you can do mathematically to solve it. That's not a good place to solve it. So technically what you're going to do is switch into the logarithm form. So one method is to take me literally. If the log or exponential base is 2, what's your logarithm base going to be? Log base 2. Logarithms are always equal to the exponent. So what's the exponent in this problem? X. So we're going to set this logarithm equal to x. And then the only number left is 64. So literally, the only thing I did is rewrite it as a logarithm. Now, what did we learn the other day in 5.3? Something called the base change. Since I do not have a base 2 button on my calculator, now some of you might find out how to do that, that's fine. But the actual base change then becomes
log 64 over log 2.
And I do ln over ln. I just write the 2 letters rather than all 3. So I do the ln of 64, and you're correct, the base 2 goes on the bottom. This is what we call an exact answer. And if you're so inclined, you can go over to your calculator and do the ln of 64 divided by the ln of 2. Make sure you close them, especially before you divide, close it, and I get 6. Now this is a good exact answer, but sometimes this turns into an approximation. Okay, so it turned out to be a nice whole number. The second method that a lot of people will do is apply a logarithm on both sides. If I apply a logarithm on both sides, what can I do with the x? I can bring it down in front. So now I have x times the ln of 2 is equal to the ln of 64. How do you get x by itself? Divide off the ln of 2. And you have what's called the base change that you found in other problems. So you can take me literally, rewrite the exponential as a logarithm. There is no base 2 button, so you do a base change. Or, over here, because that base is not nice, take a logarithm, log, or an ln to bring it down in front. Your choice, it's the same thing. Now, this one is a squish together property or write as a single logarithm. So when I put these two together, they're both base 4. So I can do log base 4. What do you do when you're subtracting?
Divide.
You divide. So I take my x and I divide by 8. This is equal to 0. Now, rewrite it as an exponential. What's my base? 4. So this is 4 to the 0 is equal to x over 8. How would you solve it? What's 4 to the 0? 4 to the 0 is 1. So now if you multiply both sides by 8, x is 8.
Wow.
So I use a property to squish them together, rewrote it, and now I have a good answer. Another method would be to take this problem, since this is a negative, what if I move it to the other side? Well, now on both sides of the equation, I have a log base 4. What am I taking the logarithm of? X and 8. What do you know about x and 8?
They're equal.
They would have to be equal based on what we call the one-to-one property.
What's that funny word you said?
Well, this one's almost identical to what we just did. Which method would you rather do, the red or the blue?
Blue.
Let's do the blue method again, because if I move that term over there, ln of x is equal to ln of 2. X has to be 2. Good. Now, remember, e is a crazy number. It's 2.718281828182. Raise it to some power to be an even 6. I mean, you can sit there and guess and check on your calculator if you want, but to get the exact value is going to be tough. What exponential base are we dealing with? E. So why not, for sure, apply the ln, the natural log, which is base e logarithm on both sides. When that exponent comes down in front, what happens to the logarithm base e of an exponential base e? What's going to happen? Chugga chugga, yes.
Yes.
It comes down in front and it's all by itself now because ln of e is, if you do ln of e on your calculator, it gives you 1. It'll undo itself. And then over here is the ln of 6. So again, this is an exact value. For most problems on the test, I'm going to be totally fine if you leave it ln of 6. That's the x is by itself, ln of 6. Some students like to approximate their answer. So if I go to my calculator and I ln the 6, I'm going to write down 1.7918. 1.7918. And this is called the approximation. And the reason why some students like to go to the approximation is they want to plug that number back into the problem. So if I go back here and I do second ln e raised, and I do the 1.7918. Because I'm rounding or using approximation, it won't be exactly 6, but it'll be really close. Right? So it's 6.000. So now I know I have the right thing. So that's why some students do like to write the approximation. They want to be able to plug that number back into their problem. So the next one is a problem where they didn't write the base. And often I see students on the exam look at this and they go, I don't know what to do. But when the base is not written in, what base is it? 10. And my suggestion is, if it's not there, let's write it. Let's write it in there to make sure we remember it. So a lot of times students will come up with a problem like this and they go, I still don't know what to do. And so I say, well, if you feel stuck, rewrite it in the other form. So if this is a logarithm, we're going to go to an exponential form. So what logarithm base are we dealing with? 10. That'll be the base of my exponential. Over and over, we've said logarithms are equal to the exponent. So -2 is my exponent. So the only thing left is x. Well, 10 to the -2?
101.
1 over 100. So that would be our final answer right there. All right, this is in the way. This is supposed to be on the next page. That one. Okay. Well, what are we going to do in example 6? Same thing.
Change it into
4 is my base. Logarithms are always equal to the exponent. So this is my exponent. And then x goes here. So what's 4 to the 5th power?
1024.
1024. And we're done.
But you can count.
We can use our basic rules, whatever. If we round, remember we're going to do at least 4 decimal places when you round. The key to a lot of the exponential problems is to make sure that the exponential base is all by itself. Right now, what is the exponential base?
5.
The 3.
5, 3.
The 3 is being raised to a power, so 3 is the base. So I have to get that by itself, so I'm going to get rid of the 5 first. And 125 divided by 5 is
25.
25. Now 3 to some power is 25 is not going to be a nice number. And is 3 a base that's on my calculator? No. So let's just jump into ln on both sides. the x comes down in front. Once the base is by itself, I can apply a logarithm to bring the exponent down in front. Or you can rewrite it in logarithmic form and do a base change. I'm doing the same thing. Now divide by ln of 3. So my x is that. And I can go to the calculator and type in ln of 25, close it, divided by ln of 3, hit enter, and it's 2.9299. 2.9299. That would be a good answer. We're going to change this one into a DIY. So I'm going to let you get that base all by itself, apply a logarithm, and then let's see what you come up with. So I'm going to pause it, you guys will work, and then we'll put the answer up. Alright, so here's what the answer is going to look like. You have to go until e. E is the base that's being raised to a power. So you have to do all this work until e is by itself. So you have to add the 5 to both sides, divide by the 6 on both sides. Now since it's in base e, notice what they wrote here, the person that did this problem. They called it log base e. What's the same thing as log base e? So what they really did is an ln and an ln on both sides. So ln here, ln there. So when that 2x comes down in front, it's just 2x equals the ln of 2 divided by 2.
Oh, you're right.
So that's an okay answer. If you want to write down the approximation, fine by me. Alright, so the next one, example 3, right? Oops, did I change? So we do the same thing. Go until your logarithm this time. It's a logarithm in the problem. Go until that's by itself. So subtract the 4. Divide by 3. Now that your logarithm is by itself, just like in the previous problem, you want to get the exponential base by itself. Now you could just rewrite it. What base are you in?
E.
So I'm just going to write a little e under here to remind us it's a base e logarithm. So we're going to go e to the 1/3 power is equal to x. Logarithms are always equal to the exponent, so that 1/3 is your exponent. Done. That's an exact value. If you want the approximation, go ahead. Second ln raised to the 1 divided by 3 power.
Double raised.
Oops. Second ln
Oh, it already does it.
1 divided by 3 power. Now remember, some of you that have the calculator, when you raise it, if you get the little caret symbol, put it in parentheses. Yes, another name for x to the 1/3 is x is the cube root of e. Absolutely. So this one should have another parentheses like right here, I guess, or they should write it 7 times. So we want to subtract the 1 first. Look for things to add or subtract. Reverse PEMDAS. So look for things to add or subtract, and you're going to have 7 times 5, 3t to the minus 4 is equal to 14. Now, order of operations, I get a lot of students that will take that 7 times 5. But order of operations, PEMDAS, what are you supposed to do first? Things that are in parentheses, then you should do the exponent. So if you don't know what 5 raised to that power is, you can't do anything. So don't multiply by 7 until you've done it, right? So you have to get rid of the 7 also. Divide by 7. And now you have 5 to the 3t minus 4 is equal to 2. Now you can go ahead and apply a logarithm to both sides. I just always apply the ln. It's on my calculator. I only have to write 2 letters. Now when you do this, this whole exponent comes down in front. And because there's more than one thing in the exponent, I'm going to put it in parentheses. And now it's just a matter of getting the t by itself. So we can go ahead, divide by the ln of 5. So now you have 3t minus 4 is equal to ln of 2 over the ln of 5. And now what do you have left to get the t by itself? Add the 4 and then divide everything by 3. So I'm going to write it like this. Add the 4, divide everything by 3. Now there's my answer. That's what's called the exact value. To a lot of people, it's a little bit tough for them to read, and I don't know that you guys fully trust that answer. So this is one that I would approximate and plug back in on the calculator. So we're going to do the ln of 2 divided by the ln of 5. ln of 2, close it, divide by the ln of 5. I got that answer. Then we're adding 4. Add 4. And then we divide it by 3. So 1.4769. 1.4769. And we have to take this and plug it all the way back into there. So when I get ready, can somebody read that to me? So it is 7 times a base of 5 that gets raised to 3. I'm just going to hit second negative because it'll put that last answer right there. Second negative minus 4. Get out of the parentheses and then what? Plus 1. When I hit enter, it should be close to 15. And because I did the exact, now if you type in the approximation, it's not going to be, but because I pasted in the full decimal, it's working. This one's not as bad as it looks because we're starting with the log base 3 on both sides. Oh. We're starting with the log base 3 on both sides. Those two things are the same. So what do you know about these two things? They're the same. So you take your 4x plus 3 and you set it equal to x plus 4. So move your x's to one side, move everything to the other, and get your answer. So I have 3x, this is gone, and this is 1. Divide by 3. Are other people getting x equals 1/3?
I am.
Good, that's what you should get.